up and ask if anybody here has heard of an app called Parallel Live, which I just found out about last night. Which, speaking of the fact that we can't see how many people are watching this stream, apparently it like fakes your audience. So it shows people that there's like 50,000 people watching your Instagram stream, so that you pretend to be famous. Wild social experiment, but not related to multimodal embeddings, at least explicitly.
Okay. Wow, that's wild. Okay, I think we're live. I can't tell who's seeing this. I know that we have one person from LinkedIn. I really have no idea how else to tell if there's anybody watching this. We have 236 people signed up, so I assume at some point people will watch this video. Okay, and then I probably also should have checked this before. Is this recording? I hope it is. Okay. All right. Well, I don't know if this is recording or not. This is our first experiment, so thanks for doing this with me, Jacob.
My pleasure.
Hello, everybody in the audience and everybody not in the audience who might be watching from some other destination or might be watching this afterwards, assuming that I do get it recorded and uploaded. Today, we're going to be talking about multimodal embeddings and how that affects multimodal RAG and stuff like that. And in particular, we're going to be using CLIP to explore this text to image kind of, there's comments. Okay, cool. Okay, so we can see that there's definitely some people who are in the audience. This is great. Okay. So yeah, we're going to be doing multimodal embeddings, and we're going to be talking about how that affects your multimodal RAG kind of stuff. Someone's getting the event will start soon. Wait for the host to start message. They can't hear me, of course. I wonder if this posts directly to LinkedIn. I don't know. Oh, okay. I have no idea how this works, so this is fun. Okay. What was I talking about? I lost my train of thought. All right. Anyway, we're just going to get started, and we're just going to start talking about RAG stuff, because that's the exciting part, and that's basically what you're here for. So, okay. So we're going to talk a little bit about RAG, and then we're going to get into multimodal and multimodal embeddings and things like that. So this is the, basically this first section here. I'm just going to cover a little bit about RAG, and then I'm going to hand it over to Jacob, and he's going to talk to you about how you can check your data quality and things like that, and then talk a little bit about embeddings, multimodal, and how you can use Voxel51 to check all of that stuff out. So the basic idea behind RAG is that you want to use your data with a large language model. And that's basically it. It's pretty much that simple. And as you build this into production, you'll face more complicated challenges, but this is the basic concept behind it. And the idea behind RAG is that what you're going to do is you're going to take your data, you're going to put it into an embeddings model like CLIP, and you're going to put it into a vector database like Milvus. And then you're going to put an LLM on top of your vector database so that when you go and you ask questions, you can ask questions to the LLM, and the LLM will formulate some way to retrieve answers from the vector database. It'll send its query to the embedding model again. The embedding model will embed that, and then it will do a similarity search in Milvus, and it will return back some top set of responses. And that's up to you. That's a hyperparameter that's up to you. And then once it gets these responses back, now it has context to answer your question. And so what it does is it takes this context and it turns all of these responses into something that's human readable, and it gives it back to you. And so the main use cases for RAG is basically factual recall. If you have an LLM, a general LLM, and you want it to operate on your data, you have to give it that context. And that's basically what RAG allows you to do. It does this forced data injection. And the other thing that RAG is nice for is cost optimization, right? So being able to get your data without having to do too many calculations is something that will save you money over time. And then I'm going to briefly cover how vectors work here so that we have an idea of what we're working with. And so vectors can work on any sorts of data. They can work on image data, they can work on text data, it doesn't really matter. For this example, what we're going to do is we're just going to look at how images and text work with with CLIP. And what happens generally is you take this vector, or you take this data, and you send it to a deep learning model. And the deep learning model is going to learn something. This is a pre-trained model, and it's going to learn something about your data. And as your data passes through each layer of the model learns something a little bit more about your data. And basically, the vector that you take is usually the second to last layer, the output from the second to last layer, because that layer has captured all of the semantic meaning the model has through all of the rest of the model. And then you're going to take that vector and you're going to put that into your vector database so that you can do RAG. However, before you can even get to doing RAG, before you can even get to using an LLM in a vector database, the most important thing that you need to think about is what is the quality of your data? And that's basically what we're going to be exploring here today. And I'm going to pass it over to Jacob so he can talk a little bit more about that.
Thanks, Eugene. So I'm going to share my screen real quick. Okay. So I'm assuming, wrong date. Yeah, 1 second.
Yes, it is April 3rd, 2024.
Yep.
So we're actually doing like 6 months in the past.
Once again, thank you so much for having me, Eugene. Always a pleasure to collaborate with you. So Eugene gave a great introduction to RAG and how it is incredibly powerful for providing context and allowing large language models to work on your data. It's great for things like working in specialized domains, for keeping models up to date without having to retrain them, and for preventing hallucinations and stuff like that. The traditional RAG, and by traditional I mean over the last couple of years, has been mostly in the text domain, but lately, we've been seeing multimodal large language models, these models that, like GPT-4 Vision or Gemini Pro Vision or Lava, that can take in images and text, or multimodal like vision and language data. And we're going to be talking about how to assess the data quality, and that's kind of what FiftyOne, the tool set that the company that I work for, Voxel51, builds, is useful for. It is for understanding your data and finding the data quality and basically improving the quality of the data so that you can then generate better models, generate better predictions and results from those models. And we're going to get into that very shortly. So our mission is to bring data quality to the world. So basically to enhance data quality and to enable data-centric workflows. Bad data is the villain of machine learning, computer vision, whatever field you're in, whether you're using state-of-the-art methods or not, bad quality data can really, really prohibit a lot of applications. And RAG happens to be one of those. So what is FiftyOne? Well, FiftyOne is an open source toolkit. Like Milvus, it is fully open source. You can check the source code. You can contribute to it. We welcome open source contributions of all kinds. And it allows you to really understand your data better, to visualize, clean, and curate, to find hidden structure, to evaluate models. And it is flexible, customizable, and connected. And one of the things that it connects to is Milvus, among other vector databases. So we're going to actually get into code and visualizing and using the FiftyOne app directly in a moment. But before I do so, just showing you a couple of highlights of overview of what FiftyOne actually does. So it allows you to filter, match, sort, and select your data, basically to curate, to find subsets of interest. So here we're looking at a detection data set. In this case, I believe it is a subset of the Microsoft MS COCO dataset. And instead of having to look through a file explorer, you can actually browse through and scroll through all these samples. And these could be images, videos, PDFs, LiDAR or radar, text data. So it could really be whatever you want. And this allows you to, using traditional techniques, filter. And as we're going to show very soon, we can also use vector search to look through your data and explore it in a more nuanced, potentially, and semantically meaningful sense, in a sense that you would not have been able to a couple of years ago. You can also do things like find duplicates, exact or approximate, So here we're looking at how unique these images are, and we're finding some duplicates and tagging them so we can improve the quality of the data. And this is useful if you're doing RAG type stuff. So you can imagine in a text context, if you have a bunch of very similar or identical text snippets, paragraphs, or chunks, and you're feeding them into the model, you may not be getting too much additional benefit from having multiple copies of one piece of text or multiple very similar pieces of text. It might be good for the model to have some diversity in the context you're feeding in, whether you're training or doing training-free methods like RAG. You can do things like add tags, metadata, and predictions. Here we're just showing a very simple example of that. You can find mistakes. So this could be useful if you, in a vision context, if you have mistaken labels and you want to correct those so you can train a better model for image classification, object detection, or something else. It could also be useful if you have, for instance, imagine a multimodal data set with images and captions, and you have some captions that don't really fit the images super well. If you want to train a multimodal model to actually do image captioning or to do via instruction tuning, some multimodal conditioned generation, you may want to improve the quality of those captions so that you can actually ensure better quality of the generation at the end of the day. And once you've found these interesting views into your data, once you've filtered, sorted, selected, removed duplicates, corrected mistakes, and all of that, you can save these views programmatically so that you can then go and visualize the same things in the future. So this basically allows you to organize the data. And again, this is not just for images. Images happen to be very visually intuitive in this sense, but you could imagine doing this for many other types of data. You can understand the data, aggregate statistics, and you can look at the data more deeply using embeddings, and that's what we're going to be talking about today. So I don't want to go too deeply into this. I'll show an example of this at the very end, but basically you can, as UGN said, you can take these models that are trained either in a pre-training sense, so trained on a large amount of data, not for a specific task, or they're trained on your specific data and are really good at that, and you take a layer from that data. If it's a pre-training model, typically it's the last layer. If it is an autoencoder or some other type of model that is trained specifically for a task, it may not be the last layer. But you take that embedding, this latent representation that encodes meaningful features of your data, and you can use those to look at the structure of the data. So in this case, we're looking at the Berkeley Deep Drive dataset. We have 10,000 images here from the validation split. We have generated embeddings for them, and then we have dimensionally reduced them using a technique called UMAP. The details are not important here, but the important thing is that this gives us a sense for the structure. We can see this clustering of night and day samples, and that seems to be the main thing that the model picked up on here. And one last little bit before we get to the actual code and the hands-on portion of this webinar, but Eugen mentioned and talked a little bit about embeddings. I won't go too deep into them, but the idea is that whatever type of data you're working with, they encode, basically an embedding is a vector that encodes some aspects, some features, some important details about your data. So in this case, we take a text, in this case it's bovine buddy say, we pass it through our embedding model, and we generate a text embedding vector, which is this dense vector in this case, but you could also have vectors of zeros and ones, which are really, really hot these days. And these encode something about your data. And the cool thing about them is that once you have these vectors, you can compare the input data. So this gives you a way to say how close is the sentence or the string of text that is a very happy person to the string of text that is a happy dog. And is that closer than, for instance, the two sentences are that is a very happy person and that is a happy person. Now, intuitively, humans would imagine that the first two are more, that these two, that is a very happy person and that is a happy person, are more similar. But this basically gives our models and downstream applications a way to understand and to make these type of decisions. The key concept here is it uses some type of metric, and vector databases like Milvus are really good at these types of things, at efficiently comparing all of these vectors so that you can semantically find the most relevant data given an input query across massive data sets. You can do the same thing with images, and in this case, we're looking at an autoencoder model. So this is looking at MNIST. So these are 32 by 32 black and white images of digits, 0 through 9, and you can pass them through a model that shrinks the representation down to a very, very small size, and then tries to expand it back out to the size that it was initially, and basically tries to do this type of compression where at the end of the day, the representation that comes out of the final layer of the network is as similar as possible to what went in. So it's like encoding it in a small amount of data and then decoding it. And in this case, the middle, so this latent representation that is two-dimensional, is what we're interested in and captures this semantic or this representational power of our data. And embeddings can also be multimodal. So there are multiple models that are very hot these days, which allow you to compare and contrast multiple types of data. In this case, on the left-hand side, we've got CLIP, which is the one we'll be talking about today. You have basically image data that goes into an image encoder and text data that goes into a text encoder. And through a contrastive pre-training process, they trained the model to align the text and image vectors, these embeddings of images and associated texts, such that the representation internally, or the representation spit out of the vector for an image of a dog, is similar to the representation that you would get if you took the text encoder and passed in the text prompt a photo of a dog. You also have things like image bind, which allow you to compare more modalities even than that. And this allows for tons of cool things like semantically searching through images, which we're going to show today, for cross-modal retrieval. I'm going to just run through this super quickly, just give you an example of what is possible with this. Hopefully the sound will come through, but the idea here is we're using image bind, we're passing in an audio file, we're embedding the audio file, and then we're using a vector database like Milvus to search against all of our image embeddings and find the images that are similar semantically to that audio clip. And you can do things like traverse the space of concepts in your data set. So you can start with an image and iteratively add textual concepts to that. And here we're adding a little bit of the concept healthy, which is a text concept, and we're adding, and we're seeing how the space of similar results changes as we do that. So we went from pizzas, we added some healthy, we got some plates of vegetables and avocado. You could add more concepts, you could add more multimodal data and go from there. So that's all the overview. We've gone through quite a bit of overview now, and it's time to get into the code. So the setup here, I'm going to be walking you guys through this notebook. I will share a copy of this notebook. UGN will send a link out to this notebook, which will be available on Google Colab after the fact. But for setup, you're going to want a few libraries installed. So we're going to install FiftyOne, which is the Python open source library that I was just showing you visuals from. And then we're going to install Milvus and PyMilvus. So the Milvus library and Python client. And then if you want to, you can also install UMapLearn, which is a library that allows you to do dimensionality reduction. So it takes these high dimensional vectors, whether they're 512 or 2048 or something even larger, and it can shrink that down while preserving both local and global structure as well as possible into a much smaller dimensional vector. And that's useful for things like visualizing the structure of your data. So you can do that. I've already run these commands, as you can see, so I'm not going to go through these installation steps. But the last thing you're going to want to install is CLIP. So I just showed you something about CLIP, but you can go to the OpenAI CLIP GitHub repo and you can check it out. This is the original source. OpenAI put out this paper, the project around contrastive language image pre-training, or CLIP, a couple of years back, and this is the official implementation. There are other models that are trained in a similar fashion, many other models these days, and some of which are better in absolute sense and better at specific things than CLIP, but we're going to keep it simple and just work with CLIP, and we're going to install this GitHub repo, and then we will be able to use CLIP. So here, as long as you have Torch and Torch Vision, which you likely will if you're working in a Google Colab notebook, you should just use this command right here, which is right here in the notebook. The last couple of things you're going to want to do for setting up are you're going to want to export the FiftyOne brain default similarity backend as Milvus. So right now that doesn't mean anything to you. That will mean something momentarily, but just trust me that you're going to want to do this. This will make Milvus the vector database by default for all of your similarity searches that you're going to want to do with FiftyOne moving forward. And then you're going to want to start the default server from Milvus. So we're going to do all of that and import some of the FiftyOne library modules, and then we're going to get started. So I'll pause a second here and keep this screen on, and I'll see if there are any questions in the chat, and then we're going to dive in and we're going to start visualizing our data, generating embeddings, doing semantic searches, creating these indexes with Milvus, and so forth and so on. So I'm going to go, let me see if I can go to the comments.
Someone has asked for the link to this notebook. Also, like, I've posted a link to the tutorial about like the first part of this. I don't know if you guys can see that in the comments either. But if you want to send me the link to this notebook, I can go post it as well.
Yeah, let me share that real quick. We
can also use this time to take any questions about CLIP, embeddings, Milvus, Voxel, RAG.
Absolutely.
Jacob's life as a senior ML engineer and research rep.
Okay, I'm just uploading it right now.
Oh, by the way, I did actually check on LinkedIn to see how many people are watching. There's like 150 people watching, so this is pretty awesome. This is a really good turnout.
Love it. Okay. And let me share this. Okay, I'm sharing in the chat. Connect to comment. All right, I'm just going to share it with you on LinkedIn, Eugen, and you can share it with people here.
All right, let's do that.
All right, so let's see if there are any questions. Okay, there's a question about using something other than CLIP, like Lava or Moondream. We're going to talk about other multimodal embedding models at the end, but there are many models that you could choose to use. And a lot of the times, really any model that is trained in a way to align the text and images in some sense. And that can be through contrastive methods or non-contrastive methods. There are many pre-training objectives that allow you to align these two modalities. And so there are a lot of contrastive language image pre-training models that are available in the open CLIP library, which Eugene, maybe you can share a link to that too. But then there's also a bunch of other models that are multimodal, which are available in the transformers library via Hugging Face. I'm going to share my screen once again, and we're going to go from here.
Quick question. So Alex, I just posted the link in the collab link into the LinkedIn comments. Can you guys see that? Hopefully they can see that.
Okay. Awesome. I'm going to assume that people can see, and I'm going to move on from here. So, so we've done this setup. We've installed the relevant libraries. We've started the Milvus server. We've imported the FiftyOne modules. So now what we're going to do is we're going to get some data. So if you're working with Torch, if you've seen like the Torch data utils, there's like built-in support for loading things like MNIST or CIFAR or common datasets and other types of modalities. FiftyOne has the same thing. We have this concept of the zoo, which has a bunch of datasets and models that already are loadable from that. So we can see some of those with this list zoo datasets command. And you can see there's things like BDD, Caltech, Coco, things like ImageNet, Kitty, Open Images. And we're going to start simple. This quick start data set is super small. It only has 200 samples. It's a subset of Coco. And we're just going to use this as a way to get familiar with the FiftyOne UI real quick. So the way that you load a dataset from the zoo is with this load zoo dataset command, and you pass in the name, which is what appears in this list over here. So we're going to load the dataset. It will download it if necessary. And here we see it was already downloaded for me. For you, it will download and then loading quick start and creating it. And then we can create a session. So here we're going to create a session object by launching the FiftyOne app, which is basically the visualizer that connects your data, like the data model, to the front end part. So it allows you to control and make changes to and visualize and understand your data via the UI. So you do that by passing in launch app, the data set. And then here we're going to do, if you're in a collab, you may want to visualize this in a cell in the notebook. So if you just pass it in without any auto equals false, then you will get the FiftyOne app in a cell output in the notebook. But for us, sometimes it's easier to just pass auto equals false so that it doesn't do that. It creates the session, it launches it, but it's going to launch it at some URL. And you can see the URL by just seeing what is the URL of the session like this. And then you can click on it and it will open up the FiftyOne app in a tab in your browser. So this is similar to what we saw in a lot of the GIFs that I showed in the slideshow, but it basically allows you to scroll through all the images or videos or point clouds or whatever else you have to look at individual images, individual predictions, to filter. So here, let's say we want to filter for just things that have a ground truth label of kite. We can do that. So now we see all of the images that had a kite in them. We can do things like, if I reset this, here we can see all of the predictions that had high confidence, for instance, because there are a lot of predictions in these data sets, in this quick start data set. So we may not necessarily want to look at all of them, which could be kind of a misrepresentation of what the model is doing at its best. We may want to choose a different cutoff at some point. We can do things like look at all of the object patches. And this is just a very minimal view of what FiftyOne can do, but this is just getting familiar with the FiftyOne app. So, okay, this is a very simple data set. We're going to look at something a little bit bigger and a little bit more interesting. So we're going to load CIFAR. So in particular, we're going to load the CIFAR 10 data set. We'll load the test split, and we're going to stop at 1,000 samples. So we are just going to load 1,000 random. So this is not going to care about the original order the samples are in. It's going to load 1,000 random samples from the data set. And now let's session.view is equal to dataset.view. Now, if we go over here, we can see a bunch of images, and these are pretty small images. The resolution is pretty bad because a lot of these are they don't have that many pixels in the width or height, and we can actually compute that if we wanted to with something like dataset.compute metadata, and we can refresh and we can see what is the width of these samples. All of these are width 32, and all of them are height 32 in this case. But we can scroll through them as we did before. We can look at what are all the birds, what are all the horses, and I hope that the point is getting across that the same is true for this data set as it was for the quick start data set. But now that we have a data set, what are we going to do with it? So it's time to go towards embeddings and connect our data to the models. So the easiest way to do this is if you're just going to worry about a single image, like forget about the entire data set and just think about one image at a time, we could just choose the first image in the data set. And as an example, you can take the first sample in the data set and print out what it looks like. And you can get the file path attribute. And then you could even visualize it with Pillow as you would normally. So you import this and you do image.open, and it's very small, but you can see the image here. And that's the same image that appears over here. But what we want to do is we want to run the CLIP model on this image. And this code, which is basically copy and pasted with slight modification from the CLIP GitHub repo, allows you to pre-process images. So here we're going to pass in, just as an example, this first image. We're going to pre-process it. And what this pre-processing does is it makes sure that the means and the variances are all correct, and the number of pixels that the model expects in the width and height are actually satisfied. And then we're going to encode the image. So we have to specify we want to use the image encoder to do that. And for the text, we need to process the text as well. So the way that transformers for text work is they tokenize the text string into a bunch of small pieces, and then with positional information about where in your sequence of tokens each of those tokens appears, they pass all of that in to the text encoder. So here you can actually see explicitly the fact that the text encoding is handled by one part of the model, and the image encoding is handled by a different part of the model. So we can do this. We could run this block right here, and we can see some probabilities here. So we gave some pretty rough labels. These are the label classes that were given in the CLIP repo, but we could choose other labels. So we could choose a car if we want to, and we'll see what happens here. So in here, because I gave a car and this is actually an image of a car, we get a probability of 0.9955 for it being a car. And what it's doing is, behind the scenes, we're taking these image features and these text features, and we are, for each of the text prompts that we have here, we are comparing that text feature vector that we generated for that text prompt, and it is comparing, in this case, via usually it does a dot product or a cosine similarity or something like that, to the image features that we generated for the image that we had, this 32 by 32 image of a car. And it is basically looking at how much is that overlap, how high is the overlap between that text features and the image features, and it is normalizing everything at the end of the day with this softmax and assigning probabilities, or treating these results as probabilities. So we can see if we had these labels that we would have probabilities of 0.9955 and then 0.0029 and 0.0014. But if we put a car and, let's say, what type of car is this? We could even say an automobile.
It's very hard to tell what kind of car that is.
Yeah, so I'm just going to say automobile. So it's another word in the same vein. And here we can see that the model is unsure, supposedly, of what this actually is, given these choices. So it's assigning some probability that it's a car, some probability that it's an automobile. Really, it's both, but we're forcing the model to choose by treating these as probabilities by normalizing everything. Basically, it's saying, I think it's one of these two, and it's definitely not this one. But you can change these. You can have as many classes as you want. And what we're seeing here is that we could use this for a type of zero-shot classification. So you could have a bunch of labels that you didn't even train the model on, and you could use these to assign initial predicted labels for every image in your dataset. But this was just for a single image, and this was the explicit version, which is showing you that you can encode images and you can encode text via different encoders. What we actually are going to do in a second is we're going to use this all implicitly. So we're going to just specify the model name and have 51. Here we have the 51 brain module, which is the thing that handles our similarity and visualization and all these other ML data analysis routines. We're going to compute similarity, which is basically generating a similarity index or using a vector database on the back end. Here we're using Milvus because we put that as our default to take all of these samples, or it could be object patches or frames in videos or something else, and it's going to associate the embedding vectors generated by the model specified here with each of those images so that we can then query. So we're going to do that in a second, but before we go with CLIP, this is what it looks like for just a traditional computer vision model. So this is a model that was trained to do traditional computer vision tasks to understand the relations between pixels, and there's no textual information involved. So here you can see it's computing these embeddings. So it's using ResNet 50. It will download the model if needed, and it is taking the dataset as input. It is storing the results of all of this in this brain key. So this allows you to access all of this in the future. And it is going to, once it creates these embeddings, generate an index over them, which we will then be able to use to search. And because this is only a visual model, we will only be able to visually search our data. We won't be able to use text yet. But in a second, when we use the CLIP model, we will be able to do both things. So it's finishing up. And it might be faster if you're using a GPU. I'm just doing this on my CPU right now, but we can go back over to the app and we can refresh. And then let's click on an image. Why don't we just stick with the first one that we had before? And we can see this button that shows up here. And this button is a sort by image similarity button. And we can click on this, show similar samples, and it's showing us the most similar samples across this entire data set. And by this data set, I mean the 1,000 samples that we started with. So it is taking the embedding vector that we generated for that image, the first image, and it is using that as a query, passing that into the similarity index that was generated with the vector database, Milvus, for this data set, and finding the most similar embedding vectors that are resulting from that, retrieving them and saying, these are the images, these are the samples that corresponded to that. And when you wrap all that up and you visualize the results, you get something that allows you to see a bunch of things that look like the original query, this car, in your app. We could do the same with other prompts as well. So let's take this one right here. And we can customize the number of results we get as well. Let's say we just want the 15 top results. We can do that. And we get a bunch of cars with, in the first few cases, people on them, but in other cases, maybe not people on them. Cool. So this in and of itself is very powerful. It allows us to understand some of the structure in our data, to find similar things, to see what our model is thinking is similar to what else. So it gives us insight into the interconnection between our model and our data, kind of a view into how our model sees the world. But we're going to go a step further by using CLIP. So here I'm going to specify this model name, and for a full list of the models that are part of the 51 model zoo, you can do the same thing that we did with the list zoo datasets. You can list zoo models, and you see a bunch of results here. And you can use any of these models by just passing in the model name. Of course, as long as these models support embeddings, so as long as they expose these vector representations associated with your data. But we're going to use CLIP, which we can see right here. And this is the CLIP with a vision transformer as the vision encoder. And this is the B32 version of it. So if you're familiar with CLIP architectures, there are other options here, and you can use those via the Open CLIP library, which I can show you guys if you want. But this is just the default one that we enable through this. So exact same syntax as we used just now, but in this case, it's going to infer, it's going to know that we mean to compute the embeddings of these images with the image encoder from CLIP. and it's still going to allow us to use the text encoder from CLIP in the future. So here we're going to do this. We're going to generate some embeddings. It should be faster for you, again, if you're using a GPU runtime on Colab. Should be pretty quick regardless, though. This is why we only had 1,000 samples. Of course, 1,000 samples doesn't show the true power of the vector database, Milvus. Milvus is great with many, many orders of magnitude more samples than this, but this is just a demo to show you how these types of things work and how you can get started exploring your data with multimodal embeddings. So this is finishing up, and we generated this. And now let's go over here, and we have this button, this magnifying glass over here, and we can type anything in here. So what this is going to do, if we click on this settings, this gear button, we can see that what it's really doing is we are able to use this functionality because we have a multimodal index on our data, which we generated and called with a brain key clip sim, so that we can now type in text and it will embed that text with the text encoder and use that as the query that it's passing into the vector database. So here I could pass in something like, let's see, what could I do? Why don't I do a puppy? So we don't just get dogs in this case. We get what dogs the clip thinks are the most puppy-ish of the dogs. So again, what it's doing is it is taking our text query, it is tokenizing the text query, passing that into the text encoder, generating a vector for that text query, and it is passing that vector into Milvus and querying with a certain K, and we can choose that K, the number of results we want to retrieve, is then associating those with the images and giving us the most similar images based on that. Now, in the notebook, I have a couple of examples of queries that I think are fun to try. So if you type something like,
oh, before we get into this, someone has asked, what similarity metric are we using here?
yeah, so I believe the default here is cosine. I know that recently, I know there's been some subtleties that have been put out there into the world about if cosine similarity is even capturing what you want it to capture. I think it does a pretty good job for these types of things. You can use dot product if you want. You can specify your default metric in via an environment variable that you export the same way we did with the default backend, or you can specify it for an individual similarity index that you're generating by just passing in metric equals. And I think if I go to the compute similarity, so this is the 51 documentation. I go to the Milvus, actually it might be in integrations and Milvus, we can see where's the metric. Yeah, so you can specify, all right, the default is dot product. We're good. But you can specify what metric you want to use if you'd like.
So I actually think that I think the clip embeddings are normalized by default.
Okay.
Normalized, yes. So normalized means that the magnitude of the embeddings, the square root of all of this, of the sum of the squares is 1. So the magnitude of all the vectors is 1. So in normalized embeddings, IP and cosine are the same.
There you go. Cool. So getting back to it, we can type in Ferrari and we get a bunch of cars because there isn't too much ambiguity around the text concept for Ferrari. But if we type in something like Mustang, we get some cars and some horses because a Mustang is a type of car, but it's also a type of horse. So there's some ambiguity there, and that the text concept kind of accounts for both of those. So there's like multiple interleaved concepts there. And we can see that this is maybe an edge case or something that we would need to think about if we were trying to build a multimodal application on top of these models. We can also search for something like just pony, and we see we get all horses. So just got a few minutes left, so I'll just show you a couple of more things that you might want to do. So we'll go back here, and now that we have these CLIP embeddings, so before I stored the embeddings, and if you're following along in the notebook, you also stored the embeddings, and we can actually see them. They should be down here. So these vectors are on our data set, as well as in the vector database. But because we stored them, we can now use them for something else. And we're going to use them to pass into a dimensionality reduction technique called UMAP. You could also use PCA, principal components analysis. You could use TSNE. You could use whatever visualization or dimensionality reduction technique you'd like. There's a lot of documentation that you can find about this. We just put out a recent tutorial about all the types of methods you could want to use and what they show you, but we're just going to do this simply. Here it is doing optimization. It's finding some good fit for this lower dimensional representation of our higher dimensional data. And we can see that it generated the results object. And we can go back to our data set, and we can open a panel of embeddings, which really what this means is just we are taking the embeddings that we used and we are visualizing them with UMAP. And we can see a two-dimensional version of or semblance of a projection of the structure of our data. We could even color it by the ground truth labels. And we can start to see how CLIP sees the world and how that maps onto the ground truth labels on our data. So here we can look at, okay, there's some clustering here. This is all the same color. These two are close to each other. So why do we think that is? And we're going to look into these in a moment, but let's just select this grouping. We can see that these are all ships, and this is kind of far away from all of the other clusters. We can see there's another cluster here that's kind of far away. And what I'm doing here is I'm just selecting, I'm like pressing, I'm clicking, and then I'm dragging, and then I'm releasing my mouse or keypad hold. And we can see this is the horses. And to get out of that view, I'm just hitting the escape button. But we have two clusters that are pretty close to each other over here. So what are they? We have some trucks and we have some automobiles. So the model CLIP is saying that the semantics of a truck are pretty similar to the semantics of an automobile, which I would be inclined to agree with. We can even look at some cases that are on the boundary. And some of these do look like they're kind of boundary-ish. So this is like a very big, and this is a very big car. They're kind of thick, which makes them look in some ways like a truck. They actually look kind of like this truck right here. And especially from a 32 by 32 image, it can be hard to differentiate these things. We can look at these different clusters over here. So this is all the puppies. And what are they close to? They're close to the cats, and so forth and so on. So you can do this. You can see what other models see in your data. So you could use the ResNet50 embeddings and do dimension reduction, and then use that visualization to understand and probe your data more as well. Or you could use a different multimodal model entirely. And the last thing that I wanted to show you, I'm not actually going to run this, but if you are so inclined, you can install the transformers library from Hugging Face, and then you can use a transformers model by passing this model name and passing the name or path, which is basically the repo ID on Hugging Face. And this is going to allow you access to all of the multimodal like text image embedding models that are on Hugging Face, on the Hugging Face hub. So I'll stop there. We're just about at 10 minutes left, so it's probably a good time to pause and take questions and reflect on all of this.
Yeah. Okay. So that was awesome. I love seeing the selector tool, and it looks like the audience also really likes seeing the selector tool. So let's see. Someone has asked, Yujin Tang, do you still have concerns with cosine similarity if you normalize the vector lengths as storage time if they aren't already, and then use dot product at retrieval? Not really. My main thing about cosine similarity is that it's very compute intensive, and it doesn't necessarily do as good of a job as dot product if you have unnormalized vectors. And then someone has asked, I think this one's for you, Jacob, if you could touch on how to do this on videos with temporal data, that would be awesome. I'm looking to extract car driving on a highway out of a bunch of advertisements or something like that.
Absolutely. So if you are just interested in the individual frames or keyframes within a video, you can pass those in as if they were images into your CLIP model, and then create an index over associating all of these frames with the sample that they're associated with. Basically, you would do a search over that, and if you tried to do that yourself, it's doable. There's a lot of housekeeping to account for, but fortunately, FiftyOne does that for you. So you can work with videos and basically generate the embeddings for all the frames in a video with FiftyOne. I can actually point you to the specific blog post where we give you the code to do just that. And the example that we had was a driving example there too, but you might want to find all the places where a car is under a bridge or in front of a stop sign or something else. And that is totally possible. Of course, it's going to be more compute intensive because you are generating these embeddings for all of the frames or just keyframes in all of your videos, which is more than if you just had an image per sample, but it is totally doable. And you could do the same thing for even objects within your images. So you could take all the object patches, the ground truth patches, prediction patches, treat each of those effectively as an image, do the pre-processing, and pass those into your image encoder and generate an index over those so that you can search for similar objects in your data set. And FiftyOne also handles that. So you can just pass in patches field equals and the name of the field that you want to generate the index over, and everything will be handled for you.
That's pretty cool. Let's see. Someone else has asked, does this work on more complex images like scientific plots, stats analysis, or financial graphs?
That is a great question. So the main thing that you have to think about here is the limitations of the model and the fact that we are just generating a simple representation. That is, the model was trained to associate captions with images or alt text with images. It wasn't trained to do in-depth analysis of images and plots and charts and things like that. I think that if you want to do more detailed and thorough investigations, I would probably suggest either using a computer vision model to first identify important things within your graphs or your like PDFs. So you could identify all of the plots, all the graphs there, all of the tables, and use the table detection and then OCR to interpret that, and then pass that into RAG with an LLM, or you could pass those images directly into a multimodal large language model like FiftyOne, which is really good at handling those types of charts. So if you go to the Adept webpage, Adept is the company that makes FiftyOne and Persimmons and a couple of other cool things. They have this FiftyOne 8B model that allows you to basically ask questions in a visual question answering sense for images that contain these plots, and it's able to do multi-step reasoning over them pretty well. So I would highly recommend using a model like that.
That's really cool. I actually haven't heard about that, the FiftyOne thing, until just now. Also find it funny they also named their other models Persimmons. Jacob, someone has asked if you can share the link to the blog. You know what? There will be a email out to everybody who signed up for the event afterwards. And I will include all of the blog links, the collab links, and everything else for this talk in that email. Yes, once Jacob shares this with me, I will send it out to everyone. Okay, so we've got about 5 minutes left here. I think we've got time to take 1 or 2 more questions. Does anybody have any other questions? Oh, someone actually found I think someone found the blog. Tips and Tricks, March 29th, 2024. At VJ, will there be a recording of it? I'm not really sure. This is my first time trying to do something on StreamYard, and I don't know if I set this up to record. So if there is a recording of it, you will get it. If not to worry. I'm sure Jacob and I will do more of these webinars in the future as well. Okay. If there are no other questions at the moment, I do have a question. I think I saw this in the comments earlier, but it's not showing up in these comments. Do you have any comments on state-of-the-art multimodal models, or other than FiftyOne? You are on mute.
Okay, I just shared the blog post with you on LinkedIn, but in terms of multimodal models that are state-of-the-art, it's all changing so quickly, and it really depends on what application you're interested in. Like, are you doing a very general thing, or are you very specifically interested in this particular task? What are your constraints in terms of budget, in terms of context length, and all of that? I'll reserve an opinion on that. I think that there are people who have played around much more with these things. One of whom is Harpreet, who is in the comments right now, and who is also a member of the Voxel51 team. But if anybody has some opinions and preferences about state-of-the-art multimodal models, please put them in the chat. Curious to hear what you think.
Oh, and Harpreet says that I think this is for VJ. You can always come back to this link and it will be here. So I guess this will be saved on LinkedIn. Once again, I have no idea. This is my first time doing LinkedIn Live as well. So yeah, we'll hope that's how that works. And we've got 3 minutes here. It doesn't look like there's any other questions. So I think we'll just wrap this up. Thank you so much for hopping on and giving this amazing presentation, Jacob. Always good to do events with you. And for everyone else, we will see you next time. There's another event that's going to be happening at the same time next week, and it's going to be with the C# team from Microsoft, and we're going to explore how you can do Gen AI with .NET. Which, I mean, I don't know about you guys, but for me, I was like, .NET, Gen AI, that's pretty interesting. So we're going to get some commentary on that. All right. Thank you guys, everyone, for being here. And thank you for the presentation again, Jacob. Peace out, everyone.
Thanks for having me. Always a pleasure.
Hell yeah.